Hi, in this video, we'll be talking more about the series solution for ODEs. So, as stated last time, a function is analytic if it has a Taylor series expansion to P that converges to P for some interval about x0. Then, so it's like this. And the point x0 is known as the ordinary point of this equation if these these functions q over p and r over capital P are analytic. Otherwise, x0 is known as a singular point. If x0 is known as an ordinary point, then P and Q are analytic and they have derivatives at x0. Because they are analytic, they have this Taylor series, so you can find the derivative at x0. And this will help us solve for the solution for the ODE, as what we have already seen previously. So we will not prove the theorem, but what's important is to note that once we have this solution and we know that capital Q over P, which is this little p, and capital R over P, which is this Q, are analytic, then we will have a general solution for this ODE in series form. And what's more, we can break this series into two series that will form the fundamental set of solutions. And the radius of convergence will be the minimum of the radius of the convergence between P and R. What's important is that the radius of convergence cannot be less than the smaller of the two radius of convergence for small p and q. So we will now see how we apply this theorem to find this radius of convergence and to find the ordinary points. So what we want is we want this equation over here. Then what's happening is we need ordinary point is when this and this are both analytic. So this is analytic and it is never zero. So P is also analytic in the whole of the real numbers. As for Q, it is analytic throughout the whole real numbers as well. So combining these two, all x in R in reals is an ordinary point. And will there exist a solution? Yes, because x0 is an ordinary point. And the lower bound of this radius of convergence, well, for Q, we know that x minus 1 and E both have convergence infinity. So Q will have also convergence infinity. As for P, we just need to write it in series form and do the ratio test to see that the radius of convergence is 1. So another useful fact in determining the useful convergence is if fx is a polynomial, then 1 over fx, the radius of convergence, will be precisely the distance from x0 to the nearest complex root of fx. So what it's saying is that, okay, we have a polynomial. We already know it is a polynomial, so like here, the denominator 1 plus x squared. So it becomes a rational function and we just need to find the complex root of fx over here. So we just need to find the complex root of fx equals to 0. After doing so, then you just take its distance from x0. So here's an example. So let's say you have a fx equals to 1 over 1 plus x squared. Then you want to find the radius of convergence. Then we know we can expand the Taylor series to form this. And we use the ratio test, which is very standard. But if we just look at the zeros of 1 plus fx, then x must equal to plus minus I. And the distance of plus minus I to 0 is 1. Hence, we see that the radius of convergence is 1. So, you can see how this is a very useful theorem to helping us to find the radius of convergence for 1 over a polynomial. Now, let's take a look at another example. So, we're supposed to find the radius of convergence of 1 over x squared minus 2x plus 1. So we observe that when this polynomial equals to 0, the complex roots are 1 plus minus I. Since the denominator cannot be 0, this establishes the bounds which the functions can be defined. So the idea now is you just take this, you take the distance to 0, which is square root 2. So for the first case, when you center about x0, the Taylor series has a radius of convergence of square root 2. When you center about x0 equals to 1, then the distance is only 1, so the radius of convergence is 1. Our last example puts everything into place, and what we see is this. We are now supposed to determine the lower bound for the radius of convergence for this equation. So what we do is write it into standard form, and we find the ordinary points first. So since x0 is an ordinary point, then it is analytic about x0 equals to 0, because px is this and qx is this. When you the 0 here doesn't make the denominators 0 or the numerators blow up, so it's still analytic about x0 equals to 0. And we already know that the complex root for 1 plus x squared is plus minus I. So the radius of convergence for both P and Q is 1. Thus, by the theorem earlier, over here, we know that the radius of convergence for the series solution is at least 1. And suppose that initial conditions y0 and y0 prime are given, then there exists a unique solution in the reals. And on the other hand, it will also guarantee that the solution will be of the form of a series solution. So what does this imply? It does not imply that the unique solution is the power series, because this radius of convergence is 1, so it only guarantees that there will be a solution of the form of the power series between -1 and 1. But we know that the unique solution must be for the whole reals. So they might not be the same but equal in value for only in -1 to 1. Because this series solution will blow up outside this range, or may blow up outside this range. So I hope now you have a better understanding of when to use the series solution and a more better understanding of the radius of convergence for analytic solutions. That's all for this video. I hope you have enjoyed it. If you have any questions, leave it in the comment sections down below and I will answer them. Please like, share and subscribe, and I'll see you again. Bye.